All right, I'm going to record this to computer so we don't have any issues because I missed it twice. Everyone's attention on this one. NA means not applicable. It means an empty cell. Never type it. Never use a zero. Never use a dot. Never use a dash. Leave it blank. Get in the habit of doing the exact same procedure every single time. There are ways of counting it in, but we just had 3 people who had problems with NA, and there was one issue with using a command drop NA with too many variables at the same time. And R created one that wasn't supposed to be there. Well, I'll get it because it is that. And then the second thing is typing in NA, especially if you do it inconsistently, where some cells are blank and when some cells are NA, creates problems. Just as a best practice, leave empty cells empty. Why don't we ever call them zero? Zero is data. It is actually saying something. So don't use zero, don't use a dash, don't use a dot, don't use an NA, just leave it blank. All right. So this again is now being recorded. Oh man. Gnarly. Tell me what to do. Tilde, beautiful. Okay, that is perfect. That is going to get us good results. But before we get that, Cassidy, please tell me what research question Niley has identified with this approach. I'm kind of cool with that. But I don't want to do that because I want to walk through the biology of that. How would a male influence the length of a female? Okay, so if that were the question, then which animal should we be looking at? The males or the dewdrops? They could be, but why are the males there? They could be what? But why are they there? They're looking to reproduce. Yes. Yeah, so let's think of the question relative to the biology of the situation. And the other thing I want you to think of from the male's perspective. Who's moving? The female or the male? The males. So the males are choosing to be somewhere. So now let's come up with a question. If that is where we want to put it, I will type it that way. The male spiders like the long lady spiders. Did I get that in my 50-year-old vernacular? Cool. So I'm good with that. We need a little bit more code. And I'm sorry, I think I stopped Niley. What else do I need? Cool. So run it. Fantastic. Yeah, it's because of the NAs. Well, we're gonna have to figure out what that is, but that's gonna have to be an individual thing. Now, so Macy, we hit enter. When we hit enter, we go from ignorance to knowledge. At this point in time, Macy, what is the first thing you focus on? The p-value. Is that a small or large p-value? It's a very small p-value. Macy, do we talk about the null hypothesis or the alternative hypothesis? The alternative hypothesis. Macy, at this point in time, would we suggest that the females are similar size? They have a male versus not, or we suggest that they are different size, they have male or not? We suggest that they are different. At this point in time, Marissa, do we have any information up here which would help us understand whether male is associated with larger females or smaller females? Right now, I would actually agree with that. You look at this, you can kind of guess at it, but no, not yet. All we could say is different. We could say that the difference is pretty big. You know, it's well beyond zero, but we can't exactly say what it is yet. We don't have medians. We don't have that information. Marissa, in order to figure out that difference, what do you want me to do? We could do a comparison. I like visuals, Marissa. Why don't we do a box plot? That is an excellent idea. Kim James, I'm actually going to give you a break in this one because you're one of the people with the bug. All right. Shia, yes, Liz. That is fine. Shia, tell me what to do. I want to make a box plot. Love it. Copy and paste all the ggplot code. Very smart indeed. So I went over to Hurricanes and I copied that code. Why don't you take me through the aesthetics? Okay, that was perfect. What is going to happen when I run this, Cameron? Lines 39 through 42. That's perfect. Let's find out. That's what we got. We got thing added into the to the environment. That is great. So now, Trevor, you weren't here. You got to be in virtual land. We're still going to tap you on this one. So what am I doing here in lines? Well, actually, what am I doing here in line 40, 44? I have a variable called toSample, and I'm just calling that variable out. So now if you can walk me through here, what am I doing in lines 45 and 46? I love that. Do I need to make any adjustment right here? I don't know. Okay, no, it's not. So why don't we run through that and make sure this all looks good? Okay, Marissa, coming back to you. We know there's a difference. Do we know what the difference is now? Tell me. Who is larger, the females with males or the females without males? Females with males. They like the long ladies, yes. They are with those. Now, Sydney, I'm going to grab you on this one. Is that a good looking variable name? What about down here? Is that an okay variable name? I like that. I want us to fix this. Do we need to fix the x-axis? No, I think we're pretty good with that. So let's get rid of it. What about the y-axis? Do we need to fix that? Tell me what to do. Love it. Thank you for in the parentheses too. Absolutely. Okay. Maybe. Is that better? Marissa, I'm coming back to you. Marissa, you've told me that the large females are associated with males. I want you to give me a nice, good biological sentence. Keep it simple, keep it clean, describe the pattern. All right, so I am totally okay with that being a figure legend when you're not describing a result. That's good. That's what you want to do with a figure legend. You just want to describe the figure, and that is a perfect way of describing it. I'm going to ask us to describe the result, though. So I asked for a slightly different thing. Macy Mullis, I'm coming back to you because you're the one who talked about the p-value. Give me a nice, simple biological sentence that describes the result. I'm totally okay with that. For right now, I'm going to leave it as a blank. I'm going to leave that as a blank. But can we put in the P? What's our P? Yes, it is. All right, should we run it? That looks good. We'll get you caught up. Good. Good. Well, show me afterwards. Take a look. We'd like to know. Okay. That is a non-parametric test. Now, let's take a look at the math. That's the math. I'm going to promise you It's the exact same structure as what we saw with the two-sample test. It's the same concept. It looks different, it operates a little differently, but the same concept. First thing, this non-parametric test calculates two test statistics. You report one of them, and you don't care which one it is. And most statistical packages will only give you one. And again, you don't care. First thing, the sum of the two statistical tests equal the product of the two sample sizes. So if you know one of them, you automatically know the other one. So that's why you don't report both of them. It doesn't mean that you know it instantaneously, you just look at it, but it's just what we use and what we report. The calculation is the sum of the ranks for one of your samples, one of your populations. Just when you sum up all the ranks, how big is that? Are they mostly the big ranks? Are they mostly the small ranks? Or are they kind of all the ranks, some small, some large, some in the middle? You sum up the ranks, and then you control it relative to your sample. Well, this is kind of what we were doing. We were talking about means, and this is kind of the concept we're talking about, variation. You're looking at the sum of the ranks relative to a control relative to the sample size. This one, this two, these are just constants for the equation. But that is the concept behind it. You do this for both populations. This could be the females without spiders, males. This could be the females with males. You do it for both of them. They give you reciprocal numbers, the difference between the product of the two sample sizes. You report one of them. If one population, like in our case, females without males, the sum of the rank is going to be pretty small. If the sample size for that is large, then together, that makes a small number. The sum of the ranks are small and the sample size is large because you're subtracting by it, you're controlling for it, you're making it relative to, then your U value, your U1 is small. If your U1 is small, what about U2? That made me giggle. If this number is small, what do you know about this one? It's large. Because again, the sum of these two have to equal the product of that. If you measure the female ranks and you sum up all those female ranks who had spiders, that's a large number relative to the sample size. Now, as a result, the second U, I got away with it this time, is large. It's the same basic concept. I do not need you to memorize these equations. I do need to understand them. In the case of the U test, you're summing up the ranks relative to the sample sizes. That will influence each measurement of U. You report one of them. Why don't you report both? Because you automatically know the other one. You don't actually, you would be able to calculate it without any additional data. You'd be able to calculate it. What you'd do is you'd find the product of the two sample sizes and then just subtract it by whatever U you measured. That's the other one. There. Can anyone see what other numbers you present? What are the other two numbers you present? You present the U value, whichever one R calculates. What are the two numbers you're going to present to get that P value? Okay, it's on the screen. N1 and N2. You represent the sample sizes. So when you report a man-Whitney U test, you report the U value, and for us, that's right here, 123.5. And you report the sample sizes. Can anyone tell me how we're going to get the sample sizes for? What's that? The sample sizes for the females with and without spiders. What code are we going to use? We're going to use count. It's called length. That's right. But you're right. You're right. What code do we get the length for each group of spiders that allow you to get a calculation of a variable relative to a group? T apply. So we do T apply. We do spider length by males length. That tells us our two population sizes. We can now represent 57. And we can run it. Yeah. Yeah, that's a good question. Because it's called a Mann-Whitney U test, but ours runs a Wilcox test. They're the exact same bloody thing. So we have now looked at two nonparametric procedures. Wilcoxon sign rank test, for me, beautifully logical. Beautifully logical. You take your expected mean, you just look at whether things are above or below it. If they're disproportionately above or they're disproportionately below, you're talking about the alternative. If it's kind of random, you talk about the null. Mann-Whitney U tests, I think, are mathematically interesting and mathematically cool, but truly stupid. I mean, just bonkers. It gives you a calculation, and the calculation you can trust, but it's so weird. You make all the data uniform, but they don't weren't uniform. They were beautiful. You said no, conform and be exactly like everything else. That's sad. You have this gorgeous variation, and you say no, make it equal. That's sad. And then individuals are forced to be tied. That's sad. It works. And yes, I will continue teaching you nonparametric procedures, but they're weird. And from now on, when you read a paper that is dated after 2010, anything beforehand, nonparametric, totally cool. But after 2010, they use a nonparametric procedure. What should you say to the author of that paper suddenly behind closed doors? Dude, what's your problem? Seriously. And we will get to much, much, much better approaches. But we will learn them. Connor? That's when the computers got strong enough and R got more common enough where you had some techniques that were much, much more suitable for data like this. Much more suitable. Cool? Any questions on that? Okay. Last question, as per usual, not for the day, just for right now. I'm Kim T. Should I be happy? Why not? I didn't save anything. I didn't save it one bloody time. I screwed up to begin with, and I screwed up now, and that's all bad. So let me save as. Let me go into my code. It is important to organize. I'm going to take this, and then I'm going to put spider, non. Cool. I am going to. That'll be the next unit. Any questions with this? Going once, going twice. All right. So we're on a new thing. What should you be doing at this point? Create a new project. So let's just go straight at that. I'm going to open up our studio. I'm going to go up to File. I'm going to go to New Project. There are a number of different ways of doing it. Take in mind. I'm going to go back down. Go. No, you're right. I'm not creating a new project. I'm wrong. I know. He's having a day. He's having a day, but I will save everything, copy it out, create a new script, and paste it. And I'm clearing out everything in between. Make sure you have that closing script. A common bug, and I think a number of people have already seen this, is when something is going on in your code that catches it in a loop, and it just won't work. Code looks right, but it just won't work. Many times, just closing out your entire R, getting rid of your environment, clearing out your projects, clearing out your packages. You run it again, and it works beautifully. This is 7C. Next thing we're going to be doing is paired tests. And personally, I like paired tests a lot. Lot. A paired test is when the data are not independent. So if the two sample tests that we talked about already required independence, a paired test is explicitly not independent. And you see paired tests in a variety of different situations. A very common form of paired tests that you see in medicine, you see in education, you see in a lot of experiments are before-after tests. You measure something beforehand, you then prescribe a treatment, and you measure that exact same thing afterwards. It's a paired test where you want to know the change in each individual participant, whether it be a spider, whether it be a cancer patient, whatever it might be. You want to know that individual's response. There are other types of paired measurements, and these show up a lot in like developmental studies, where you measure at one stage of development, and then you take another measurement of that exact same individual at another stage in its development. That is paired. That same individual is being measured twice. And then you can have consecutive measurements. You are participating in one. I measure you at the beginning of class. I measure you at the end of the semester. And I want to know the individual differences as they relate to the collective whole. So if the two sample test, independent data, the man-Whitney test, independent data, paired tests are non-independent, and that is a good thing. Technically, and this is a lot like what we've been saying quite a bit, you can run a traditional two sample test with paired data, technically. It's not appropriate, but you could definitely do it. I want you guys to have some conversation about what would be lost if you did it. You can also modify the data and run it as a one sample test or a Wilcoxon sign rank test, where you take like the pre-post and you look at the difference between the two, and then you just measure the difference. Again, what would be lost by that approach? All right, let me give you about 3, 4, 5 minutes, and then we'll come back with that. Logan. Oh, Logan's not here right now. He already told me. Aaron. I already called you today, didn't I? I'm calling you again because for some reason now you're at the bottom of the list and you were not at the top of the list. I don't know what happened. Aaron. What is the problem or what could be lost if you don't treat the data as paired? Cool. So that's your population of pre. That's your population of post. Right now, Aaron, is there any difference at all? Really? 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 Is there a lot of variation in this data? There's a ton of variation in this data. Oh, dear Lord, you got to kill me. Is there a lot of variation in that data? Is there a clear? Dear Lord, do you know what variation is? You're just messing with me. Is there a lot of variation in this data? No, very low variation in this data. Is there a clear difference in these data? There's a clear difference in those data. I'm going back to this one. No variation. Nada. There's very low variation, right? Is there a clear difference in these two group populations? Yes. Not variation, very low variation. A lot of difference. What about these data? I'm going to have to reduce all of your grades by grade is what I'm feeling. I'm just saying. Come on. Come on. There's a ton of variation in these data. No difference, at least no perceived difference, correct? Correct? I don't think y'all believe me on this. I think you just accepted the fact this is what I want to hear, and we're going to placate the old man. Y'all suck. All right. These are paired data. When you do not pair them, do you see the pattern? When the data are paired and you actually see the change in each individual, is there a pattern? Actually, dramatically. And is there a lot of variation in that pattern in the sense of, are these slopes dramatically different than each other? No, the slopes are actually very uniform. And there's a clear pattern in that everyone's statistical anxiety, probably not today, is going to be reduced. But that is only observable once it's paired. Before it was paired, the whole thing is washed out because of all those differences in those individuals, as was stated, is washed out. Does that make sense? This will work converting the data to a one sample. But it's weird and desperately unnecessary. So don't. When it's not paired, there's a lot of variation. When it was paired, there's very little variation. All the slopes are basically the exact same. And all the slopes are going down. Every individual appears to be responding the exact same way. Yeah, it's measuring the difference. So each of these would be negative, and they'd be negative by roughly the same value. You can do it, but it's kind of weird, and it's definitely unnecessary. And it's actually harder than not doing it until you graph it. We'll get there. Cool. Okay, in R, very simple. All you have to do is run a t-test and just add the line, paired equals true. Grab the data, watch density, not yet, let me explain the experiment first. Grab the data, watch density, take a look at the data sheet, get a sense for what it is doing. This is an experiment. We ran these same wasps we talked about earlier in the year. They can start up nest as social females. They can start up nest as group females. And we were interested in why a female would give up fitness in order to be in a group nest. When she's by herself, she lays every egg. When she's in a group, maybe does, maybe doesn't. So we ran an experiment, and what you're looking at here is you're looking at palms from a top-down view. Yes, this is an illustration I made, and yes, someone actually published it as that illustration. I just want you to know, stick figures work. This is a top-down view of palm trees, and what we did is we measured the proportion of social and solitary female at each tree, where each tree has multiple nests, 2, 10, 20. There are lots and lots of these nests in these trees. We measured how many palm fronds there were, because on average, there tends to be one nest per frond, rarely any more than that. And we treated each frond as a nesting site so we can measure density. How many nests you have per tree is how many nests you have per frond at that tree. We then remove fronds. And the experiment where we increased density, we removed those fronds and we took them away. So we reduced the number of nesting sites by half. And the control, we removed the fronds and then we put them back on. We literally cut them off and then we use a hammer to hammer them back on. And then we let them nest for 2 weeks. So this is a paired test. We have the proportion of solitary females beforehand, and then we have the proportion of solitary females afterwards for these two experiments. One experimental treatment, the other one a control. Make sense? Okay, now grab the Excel file, take a look at the data, get it into R, run the t-test as a paired test. All right. Liz? How you doing? Yeah. Liz? I'd like you to give me a nice little result sentence for the control. So I just ran lines 17 and 18, which compares the proportion of solitary females relative to before and after the experiment. I'll put a little question up here because it's always a good idea. How does the proportion of solitary females change when the number of nesting sites stays the same, i.e. control. Okay? Keep going. Great, so keep going. Perfect, perfect. Everything about that was perfect. And the way you went about that was perfect. P-value is large, therefore you describe the null. Go back to your question, now restate the question as a statement. The proportion of solitary females does not change. I love that. So let's copy out our data, because that's always good. Let's put it in the right spot. Let's hashtag it. Let's write our sentence. Love it. And then, Danny, what's my evidence? Round it. It's way too precise after that. Seven, 1, 2. I like 3 decimal points. This is a simple convention. Love it. All that was perfect. It's a beautiful result sentence. Simple, clean. Are we saying that we failed to demonstrate significance? No, we're just talking about the biology. The biology is cool. Do we want to see a difference in the control? No, that would be weird. That would make us unhappy. Nothing should happen. That's kind of what we want to control for, right? Nothing happened. Yay, we won. That was weird. There was a little echo on there. All right, so we're going to finish up the last little part. We run that. We copy out this. We save it. And I ask, Galen, coincidentally. Same thing. This is for increased density. Start with something. Start with the p-value. What do we say? P-value is small, therefore what do we describe? Okay, and now give me a very simple result sentence. Done. When density is increased. Portion of solitary females changes when density increases. We will start from here on Thursday. This is a perfect stopping point. Honors, graduate students, stick around for probably about 15 minutes. Everyone else, have a lovely day. As I save this to make sure we got it. No tripping. It's going to take me a little time to get it up there. And now, since I didn't get to do what I wanted to do, probably take me until tomorrow. But yeah.